In this video, we're going to be looking at the mechanisms of some reactions of benzene. So the first of these we're going to look at is the nitration of benzene. So this is where we have our benzene molecule and we're adding an NO2 group, a nitro group, to the benzene. Now the reagents we need to do this are concentrated nitric acid and concentrated sulfuric acid. So the first step we need to do is create our electrophile, which is this NO2 group that's going to add on to the benzene. So to do that, we react together our two acids. And this is going to generate NO2 plus HSO4 minus and water. Now at A level you just need to know this step in the mechanism, but I think it can be helpful to know how these products arise from these reagents. So in this next part I'm going to explain that. You don't need to know it for A level, but I think it's interesting. So first I'm going to draw out the full structures of our reactants. So this is the nitric acid, and this is the sulfuric acid. I've just drawn it out to show this bond because we're going to use it in a moment, but it's identical to what we have over here. So the first step, we've got the lone pair on this oxygen pulling off the proton from the sulfuric acid, and that causes this bond to break and go on to the oxygen. That produces these products. So this oxygen now has an extra proton. And over here we have the sulfuric acid without that proton. So this molecule here is the HSO4 minus that we wrote up here. In the next step, the lone pair on this oxygen is going to push out the OH2, which is now a very good leaving group because it's got this extra proton and positive charge. And that produces our electrophile NO2 plus and water. So these products here are the NO2 plus and the H2O that we wrote up here. So as I said, you don't need to know this full mechanism in blue for A level, but you do need to know the overall equation at the top. So now we have our electrophile. We need to react it with the benzene. Now the mechanism for this involves going from the circle, attacking the nitrogen with the positive charge. Now this is going to lead to the nitrogen being attached to the benzene ring, but we still have a hydrogen from before. So now this carbon is no longer involved in the delocalized pi system because it's using all four of its electrons to form sigma bonds. So that means we draw the rest of the delocalized pi system as a kind of horseshoe shape with a positive charge in the middle. So the positive charge is from the electrons being taken out of the delocalized pi system. And the horseshoe structure, it's important that that only goes from this carbon to this carbon and doesn't extend anywhere near this one. So our next curly arrow is from this bond going towards the positive charge, so we're reforming the delocalized pi system, and this is going to make our delocalized system with the nitro group attached, and this H has just fallen off as an H+. Now the final step we need to consider is regenerating our catalyst, which is the H2SO4. So we're going to take our proton that we just generated and combine it with the HSO4- that we produced in the first step to make our H2SO4. The next example we're going to look at is halogenation of benzene, which follows a very similar kind of pattern. So as before, our first step is generating the electrophile. So we're going to start with Br2 and we're going to react it this time with FeBr3, which is a halogen carrier, and this breaks open the bromine bond to form a Br plus and FeBr4-. Then we want to take the electrophile that we've just generated and react it with the benzene. So as before, our arrow starts from the circle and attacks the electrophile. This is going to make this with our horseshoe shape and the positive charge. Then the carbon-hydrogen bond is going to break and the electrons are going to go towards the centre, which will reform our delocalized pi system, this time with the bromine attached, and we've got an H+ produced as well. Then the final step is regenerating our catalyst, the FeBr3. So to do that, we take the H+ that we just made and we react it with the FeBr4- that we made in the first step to produce HBr and FeBr3. The third example we're going to look at is acylation. So for this, as before, our first step is generating the electrophile. So let's say we're starting off with this molecule. This is an acyl chloride or an acid chloride, and we're going to react that with a halogen carrier, in this case AlCl3, and that's going to pull off this chlorine to make this with a positive charge there and an AlCl4-. So now we have our electrophile. We're going to react that with benzene. Like this. And that's going to make this. So we're attaching our electrophile to the benzene ring via the carbon with the positive charge. And as before, this is going to have the horseshoe with the positive charge. Then the CH bond breaks to make this, which is our product. And to regenerate the catalyst, we just do the same as before, react H+ with AlCl4- to give us HCl and AlCl3. So hopefully from this you're starting to see the pattern. So we can write out a general mechanism for electrophilic substitution reactions. So assuming that you've found a way to generate your electrophile, you then react it with benzene like this. So your arrow goes from the delocalized system attacking your electrophile. Then you make your intermediate with the horseshoe structure. Then your carbon-hydrogen bond breaks and the electrons go into the centre, and you're left with a benzene ring with its delocalised system and the electrophile plus a hydrogen ion. So we can see why it's called an electrophilic substitution mechanism. So it's electrophilic because it's involving an electrophile, and it's a substitution because we're substituting the hydrogen that was here for the electrophile. If you found this video helpful, please like and subscribe. My next video is all about phenol, so if you want to check that out, there'll be a link in the description.